go on collabresearchgoogle.com. I hope you're seeing my, yeah. And then here, a file open notebook. And then here, go on GitHub. And we will search for EML community, like you did for the intro tutorial. And this will show you the tutorials that are available for in this repo. And please choose Resnet 18 CFAR 10 baseline. And this kind of gives the whole, gives away the topic in this part of the tutorial. Okay, so today we are going to code some exercises related to supervised learning, and we will start with a simple baseline, Resnet 18 classifier, and we will train it on CFAR 10. Due to the constraints of the setting using a collab, we cannot run on very large data sets or using very large models. But all the concepts, all the ideas that we were presenting, they are applicable to larger models as well. So yeah, so I hope everybody managed to retrieve this the first part of the tutorial. So in supervised learning, generally the goal is you're given a large number of pairs, inputs and labels, and then we want to train a function that maps inputs to the correct labels, and this is supervised learning. And here we will see like how we can implement such a function. And so the hope is that we train on a training set, but then that this would generalize well on unseen data during training. And so this is the first part. So we will just be looking at a basic image classifier trained on CFAR 10. We will not have time to train it fully because yeah, it would take some time. But at least we will have the time. We will run a few iterations and we will see that the loss starts going down. In this part, the coding, there's a coding exercise where you have to implement a bit of the Resnet module. And then in the second part, we will have, Carl will be presenting the adversarial attack on this classifier to highlight some of the issues. And then in the third part, we will be looking at self-attention. So, okay, so I guess we could just start. Let me see if there are quite a few messages. I will just check that, and then we'll continue with the code. So I hope the teaching assistants are online, and then they can help with the questions that appear. So okay, so to run the collabs, you need first to connect to a runtime. Okay, I'm not signing in because I'm no. And incognito. Okay, so we're now connecting to the runtime. So we will select, if it's not already selected, we want a runtime with a virtual machine with a GPU. So we are connected. So to run a cell, okay.
Viorica, we do have a request to zoom in a little bit on the code.
Let me see if that works. So I hope you all managed to download to connect to the GitHub, so then you have it on your own screens. Okay, so I am now connected to a GPU, so I have the confirmation here. Yeah, and then we are just here. We are just defining some useful types. Okay, let me see how. So yeah, basically, as I said, the baseline that we are using is a Resnet 18. We could have like maybe more standard is a Resnet 50 or a Resnet 101, but like for because we are quite limited in terms of resources, we will use a Resnet 18. So Razvan mentioned this morning this type of models, the Resnet models. So as you probably know, like Resnet allows you to learn an additive residual function with respect to the representation computed by the previous layer. And actually, this is very useful because it makes gradient propagation much easier. So, and then we can train much deeper models. And we will use here Resnet V2 because the authors have shown empirically that you can get better results with V2 compared to V1. So you might know, like in V2, actually the difference is that you can obtain a full identity chain over the network, whereas in V1 we had the nonlinearity after the summation, so that then you would not have the identity anymore. So in V2, because we have this skip connection all the way, this makes it easier for gradients to propagate. So yeah, let's go a bit through the code. So as I said, we will be using CIFAR10, which is like the MNIST of real images. It contains 10 classes of low-res natural images. And you can see there the classes: airplane, automobile, bird, cat, and so on. We will visualize these classes later on, and we will see what they look like. And as usual, we define train and test sets such that yeah, we can test for generalization by running evaluation on the test set. Okay, so I will be running. So next we define some hyperparameters for the training, like batch size, and some parameters for the batch norm. So I think there were some questions in the morning, for example, about batch norm, but we could discuss a bit once we go a bit through the code. We could discuss like what are the different types of batch norm of normalization that could be used and why do we use them. Okay, so here we're just loading the data set. So for data set loading and pre-processing, we are going to still be using TensorFlow. But for the rest, we are using JAX and Haiku. So JAX does not offer support for data pre-processing and loading because TensorFlow has done already a pretty good job at that. So there was no point in replicating again the effort. So yeah, so here in this part we are still using TensorFlow. So here, as you can see, we are loading the data set, and we are applying some pre-processing. So during training, we need to shuffle the data. It was mentioned in the morning that this is important during training to shuffle so that the training does not learn some weird features depending on the order of the samples. And then in pre-processing of the images, basically we are just converting the images to float, and then we are normalizing the images. So these images are in 0 to 5.5, but to improve stability of training, it's better that we normalize them in -1.1. So this is what we are doing in the pre-processing. And then during training, we also apply random flip, left, right. So this is a sort of data augmentation and this generally improves performance. And we take random crops such that we make the network more invariant to translations of the objects. Okay, so let me run this cell. Okay. So here I have a function to display images. It's a simple function, but we will use it. We will call it later on. And then here we have the Resnet blocks. And this is the first coding exercise for you. So basically here, let me see, yeah. So in JAX, so this is JAX with Haiku. So Haiku is an object-oriented library on top of Haiku. So we are defining our modules as classes. So here I've given the code for the Resnet block, but I've only defined the layers that need to go into a Resnet block. I did not connect them. So the blocks, we need to define them in the init function of the class, and then to put them together, we do this in the call function. And I let you as task to put them together in the call function. So this is your first coding exercise. I hope things are fairly clear, but I'm not sure. I will check. So we have a question. Why? I just seen now a random question. I don't know if there are probably there are three. Okay, I am just going to go through some of the questions. Which file do we need to open? So please open the baseline. So it's the Resnet 18 CFAR10 baseline. We are starting with that one, and then we will continue after that with the other parts. Would you write the exercise? I'm not sure what that means. So the exercise is you need there. It's now on the screen where you need to put the code. So why do we scale to -1, 1 and not 0, 1? So in general, it's better to scale the inputs to have 0 mean and unit variance. So I think we get slightly better results by scaling to -1, 1 instead of 0, 1. Carl, what do you generally use for this? What kind of normalization do you prefer?
Yeah, so I think after the appearance of batch norm, it kind of stopped mattering quite so much. But especially in the very early days when, before we were using batch norm, there was this problem that kind of when you look at how the gradients work, if you have this big convnet, you can change the output quite a bit by changing sort of the mean value of conv1, and it was basically shown that if all of your inputs were greater than 0, basically, but in the range 0 to 1, then you're kind of biasing the gradients at conv1, and this actually increases the variance of the gradients as they are applied to the weights down at conv1. And so basically all of these early efforts to center the inputs are aimed at making the gradients better conditioned and making it so that they're sort of the gradients themselves are mean 0. And this just empirically led to much more stable training. Of course, once you have batch norm, any bias in the input is going to be removed after the first layer because you do mean subtraction. And so the result is that it kind of doesn't matter as much, but I think it still does matter a little bit. And so really it's just an empirical result.
Yeah. Okay, let's see what other questions we have here. So yeah, just as I mentioned, so if you just look to the code, like the layers are defined for each block. So we have, so okay, let's look over the block. Maybe it would help. So this is the Resnet V2. So in Resnet V2, we use the so-called pre-activation, which means that we apply batch norm and ReLU before the convolutional layer. So first we have to put B and ReLU, and then we apply the convolution. And we have two such units in each residual unit. And then to reduce the number of parameters, in the paper, the authors propose actually to use this bottleneck, where instead of using these 2 convolutional layers, which were each 3 by 3, you can use three convolutional layer, but one with 1x1 filter, and then 3x3 and 1x1. And this is what we call the projection conv. If we first project into a lower dimensional space, and then we apply there 3D convolution, 3x3 convolutions, and then we project back to the original space dimension. Also, like in this, so as you probably know, you can apply a residual. The input and the output must have the same dimensions. So, but if we want to have, if we want to increase the number of channels, then we have to use. Then we can use here on the connection. We use a 1x1, 1x1 convolution to increase the dimension. So basically here in the init, we've defined all the blocks that are needed. So if we choose to, so we have here the parameters for bash norm. If we choose to use projection, then this is the layer that goes, the 1x1 layer that would go here, and then we have the convolutional layers defined. Bash norm, and then convolution again, bash norm. And we are just combining these layers into a tuple so that we can loop through over them easier later on. And then if we apply the bottleneck that I mentioned, then we also need to have this this other layer, again with stripe, with a kernel shape of 1. Okay, and then so all the layers are defined. You just need to connect them here. I will just check for other questions. Probably we can give a bit of time for. So in terms of batch normalization, so there are, yeah, let's maybe mention about initialization and batch norm, but maybe I'll just give a bit of time for people to try to write the code. So maybe just to give a bit of help in case, yeah, this helps. For example, here, first to connect the batch norm, for example. You just apply. So we are just looping through the layers in the list that we've defined here, and we start by applying batch norm. And we need to, for batch norm, we need to pass training and test local stats as parameters. So test local stats indicates if during testing we want to use the training statistics that were accumulated during training, or if we want to use the the local statistics of the test batch. So here I've applied batch norm, and next we need to apply ReLU. So again, yeah, I see there are questions about the parameters of batch norm, is training, and test local stats. As I mentioned, so a batch norm has different behaviors during training and during testing. So during training, we need to update statistics. So in batch norm, we generally normalize the activations by computing statistics over the median batches, and then we compute mean and variance, and we subtract the mean, and we divide by the standard deviation, such that we obtain activations with zero mean and unit standard deviation. So, and to compute the statistics during training, we take mini batches and we compute the statistics, and then we average them, like using exponential moving averages. We average over the training, and then at test time we can use this statistics to normalize the mini batches. And in this case, we set test local stats to false. Or if we want to use the local statistic, then we would set test local stats to true. Okay, I hope this is answering the question that I'm seeing in the channel. How does the image on the right fit in the architecture shown on the left? Okay, I might have answered this question, but just to... So normally the original Resnet block had 2 convolutional layers, so this would be like 3x3 convolutions, but that is quite expensive in computation. So then we can replace that 2 by 2 with 3 layers, but which are smaller. So we have this 1x1 first to project in a lower dimensional space, and then we apply the 3x3 in this in this smaller space, and then we project back to the input. So basically, this we have 3 layers now. Okay. Why do you separate all the flags? Why not use a single dict with all the flags? Sure, this is just an implementation aspect. We could use a dictionary as well. So maybe, Carl, do you want to discuss a bit about batch norm or like different types of normalization if while people are still trying to implement some parts?
Sure. So batch norm is really about preventing this problem of exploding or vanishing gradients. So what tends to happen if you just implement a neural network naively is that if the output variance of each layer is slightly smaller or slightly larger than the input variance, then you tend to have activations that go towards 0 later in the network, or they tend to explode later in the network. And then, of course, you get gradients that also explode or vanish just because the changes with respect to the output are large or small relative to the changes with respect to the input. So batch norm is essentially trying to make sure that the variance of every layer is staying the same throughout the network. And you do this by just coming up with, for every channel in the network, a multiplicative factor and an additive factor, such that the output is mean 0 and variance 1 across an entire batch. And so this means that kind of the variance throughout the network is staying the same, and this helps ensure that gradients can propagate from one end of the network to the other. There's, of course, many different other approaches, and it's kind of an active area of research right now to try to come up with the best formulation that will sort of make learning as good as possible and also potentially even help with generalization. I think that the generalization aspects of normalization are not as well understood as the optimization effects. But there's a number of other ways that you can compute those, the additive factor and the multiplicative factor that that work to lesser or greater extents. One popular one is called layer normalization, where you just compute you ensure that the mean and variance is 0 and 1 for every example within the batch across all channels. So you're computing your mean and variance statistics across all channels within a single example, and you have different means and variances for different examples. Whereas for batch norm, it's different means and variances for different channels, but it's the same across the entire batch. And in general, batch norm works better than layer norm, but it has this kind of annoying property that you have to feed in an entire batch in order to make it work. And so you have, in order to make it work at test time, you need to compute these sort of average mean and variance statistics that you can apply to test examples. And it turns out that that's actually pretty annoying to keep track of. And in this tutorial, it's the reason why we have this whole state that you have to keep track of that's separate from the parameters, which are like the weights of the conv layers. And then there's a separate learning rule by which you're learning or you're keeping a moving average of the mean and variance for every layer.
Yeah, so there are many flavors of batch norm of normalization. So yeah, as Carl mentioned, the layer norm as well. Then there are like instance normalization, group normalization. So think of the feature volume, and then you can think of all the possible dimensions along which you can actually normalize to compute features. Okay, there's a question. The purpose of 1-by-1 convolution is to reduce dimensionality, but again, we have 1+1 with higher dimensionality. What is the purpose of the second one? So, I guess we don't want to reduce the expressivity of the network. We want to just obtain the same similar representation power, but using less computation, less parameters. So by reducing dimensionality, we will apply the 3-by-3 convolution in a smaller space, and then we want to continue in the larger space of the computation. So that's why we need to go back to the initial dimension space. That makes sense. So basically, yeah, we've gained inside the ResNet block. We've gained when we applied the 3x3. It's applied on a much thinner feature maps by doing this projection. Okay, so I've put in the code for batch norm and ReLU. I will just add now the convolutions. Hopefully you've implemented this on your own. So here on the shortcut, so if we do use a projection like on the shortcut connection, and only for the first like immediately when we enter the block, there we apply this this projection convolution on the shortcut, and then for the rest of the layers, we just apply the convolution on the residual path of the network. So this is more or less what the code looks like. Let me see if I can actually run this. Hopefully I can. Okay, so I've defined this. So be careful. After this, there is a form with the hidden code. The cell that says chain ResNet blocks and define ResNet 18. That is not just a text. That is a form. So if you double click on it, it will show you all the code that is behind it. But you don't need to implement here anything. That's why the code was hidden. So here basically, now we've defined one ResNet block, and then we are just chaining them together, and we are actually building the ResNet 18. So I will just run this. The rest is very similar to what we've seen for the MNIST exercise. In the intro tutorial, the classifier there was an MLP, a 3-layer MLP. Here we have the ResNet, but like the setting up the forward path of the network and the optimizer, they're very similar to the intro tutorial. And yeah, we define the loss function as before. We use the cross entropy for classification and then weight decay for regularization. And then we define the training step. So here in the training step, retrieving the training data set will take like 1 minute, I hope not more. So we are basically now downloading the CIFAR10 data set. To train it. Okay, I hope this works. So next we define the evaluation. Let's see if I... Okay, there seem to be some download errors. So maybe please try again. Maybe there are many connections now at the same time. So we also have the function that we've seen in the intro tutorial to get the number of parameters, just to have an idea of how large the model is. So yeah, in my case, and I hope in your case as well, we have like 11 million parameters, more or less. So I am now displaying the one batch from the training set. I just work for you as well, so you can see the different classes that we have in C-Part10. So here we're just calling that gallery function to display. So yes, if you have download error, please just try again. It should work. And okay, and I will just launch just a bit of the training just to see how that it works, and then we can move on to the second part. Okay, so at iteration 0, not surprisingly, the accuracy is 0.14, which is close to the random classifier. So this is at iteration 0. The model has not been trained yet, so it's this accuracy is normal. But as we start training, this should improve. So in my case, as you can see, the loss goes down. So that's a good sign. Okay, we have a question, Carl. I don't know if you want to try and answer. Why do we use JAX instead of TensorFlow or PyTorch? So the first, let's say, the first reason is that we were hoping that JAX is more accessible for beginners, because JAX is supposed to be very close to Python and NumPy, and the library is very lightweight, and it should be easy to work with it, and it's also very efficient. We've used the TensorFlow in the past. People were complaining about it as well. So yeah, I think it's hard to find something that works for everyone. And one thing for PyTorch, yeah, we know that it's quite popular, but most of the tutorial leads we are using JAX or TensorFlow now. So it would be quite an effort for us to put together the tutorials in PyTorch. I don't, Carl, do you want to give extra?
No, I think that pretty much sums up my understanding as well, that there's quite a bit of complexity in TensorFlow, especially since we're kind of halfway in the transition between TensorFlow 1 and TensorFlow 2 right now. PyTorch would be a good choice as well because it's popular, but I don't know PyTorch. I have some experience with JAX, however. Of course, most of my experience is in TensorFlow, and I agree that there are a number of things that are rather obtuse about TensorFlow. In particular, in TensorFlow, there's kind of a lot of hidden state in the sense that you're creating a graph and you're creating these variables that kind of live in this abstract space, and you have to access them through various methods that it's not always clear exactly what they're doing, and it's easy to kind of lose track of what that state is, and that can make things rather difficult to debug. And one of the nice things about JAX is really that it makes all of the state quite explicit. You notice that you're using functions that take in the parameters and the state of the optimizer, and that those variables contain the entire state of the optimization that you're running. And so it's easy to kind of stop this process and investigate what's going on, and it's explicit how everything is happening. So in many ways, I do think that's a nice thing for at least teaching with JAX, and hopefully it also helps with actually making research code and even production code that's easier to understand and debug.
So yeah, just update like my evaluation accuracy at 2,000 iterations is already at 74%. So that's pretty good. So yeah, definitely with 400,000 iterations, it's quite a lot. But like if you want to get the accuracy that gets published in a paper, you kind of have to run on many iterations.
Yeah, so someone asked, what do we use for research? Right now, I'm mostly using TensorFlow 1, but in practice, I tend to use whatever framework has most of the code written that I need. So, previously I just kind of wanted to build on an existing code base that was written in TensorFlow 1. And so I just continued with that because it was not worth it to me to port that to something else. And plus it makes it easier to integrate with other people working on similar code bases. That said, for other projects, I'm using JAX. Those are kind of my more side projects. Some folks are using JAX as well, and so I'm building on that. So yeah, I think it really is kind of a per project decision which framework is going to be the best one.
Yeah, same here. I've been using mostly TensorFlow 1 and transitioning to JAX now.
I should say that that question also mentioned something about speed constraints. And to be honest, the differences in speed aren't that huge between the frameworks at the moment. Of course, it depends exactly what you're trying to do. I think TensorFlow right now is a little bit better than other frameworks at sort of compiling your code and getting a graph that runs fast if it has a very large number of nodes in it. But for something like computer vision, most of the time is actually spent in these big convolutions, and the sort of time spent in the framework is not very large. So for something like this, I wouldn't expect to see big differences between the different frameworks. TensorFlow and JAX both use a library called XLA under the hood, which is basically taking these high-level definitions of you have this convolution kernel and you're running it against this large tensor, and it's converting that into machine code that runs very fast on whatever accelerator you have available. And so for much of that, it's going to be the same for TensorFlow versus JAX.
Okay, so I think there's a question how to deal with code that is written in PyTorch, but want to reproduce it using other framework. I'm not sure if the question is related to converting checkpoints, or because I think this is possible. Like there are functionalities implemented to convert between checkpoints such that you don't have to retrain in every new framework.
Yeah, and I think that for most frameworks, the kind of basic operations that you have available, the cons and the nonlinearities and so forth, are going to be available across different frameworks. And so, at least for relatively simple models, you can just kind of go through line by line and convert it. It takes time to do this, but it can generally be done. Of course, there are some cases where the implementations under the hood will be slightly different, and the result is that you have slightly different numerical properties. And so you'll run the optimization on one framework versus the other, and you'll get slightly different results. I do remember hearing a few years ago that you get a few percent different, doing PyTorch versus TensorFlow, like in terms of final performance. But I've heard less of that more recently. So yeah, I think that in most cases it's probably going to work, but I wouldn't want to guarantee that any particular model you would have in one framework you can just easily port it to another, because there may be numerical differences.
Right. Okay. Maybe we should switch to the second part. So
Okay.
yeah, I think my training is working fine. I've just stopped it now, but it got to 80% already, so that looks pretty good. So Carl, if you could share your screen, I will just stop
Sure.
sharing mine.
Okay. Hopefully this is the right one. Oh no, that's not the right one. Sorry about this. Somehow I assumed the tabs would be in the same order on my Chrome
Maybe
window as they are in this list of...
you could just repeat what I did, if not to retrieve it from GitHub, if you prefer. Okay.
All right, I think I'll just do it this way.
I am sure anyway that people will not.
So hopefully you can see my screen now.
Yes, I think that is.
A little bigger. Okay, so this is what are called adversarial examples, and this was discovered in sorry. It was discovered in about 2013, which is soon after the deep networks had won the ImageNet challenge, and they were starting to take off, and people were sort of playing with ways to visualize what neural networks were actually doing. And so they tried doing things like taking the output of the network and backpropagating the gradients and seeing like what, how can you change the image to optimize for a particular category? And this is pretty straightforward to do in a neural network framework. But what they discovered is that it turns out there's ways that you can alter an image that are more or less undetectable to human eyes, but yet they change the category produced by a neural network. And so you can create kind of absurd examples where a person would look at it and it's clearly a bus, but you put it into a neural network and the neural network outputs that it's an ostrich. It works by just optimizing the image to find a perturbation which is small, but it maximizes the change in the neural network output, which of course is found by computing that gradient through the network. So in practical scenarios where there might be an adversary, this is actually a huge problem in the industry. So for example, imagine you want to create a video sharing service and you want to filter out explicit content, so that children can use this video service, but you still want to allow people to upload. Well, if people have one of these adversarial algorithms, they can take an explicit video, alter it so that it doesn't look like an explicit video to the content filters, and then it will get served, and that creates a problem. And so there's lots of examples of like situations where you have an adversary. For example, a self-driving car on the road, if there's some way of altering the signs in an undetectable way that causes cars to crash, that's also not a good thing. Now, there's an argument in the community that actually this is kind of a bad thing for the neural network as kind of a general purpose algorithm for computer vision. It sort of suggests that maybe neural networks are doing something that's fundamentally different from people, and therefore they may never match the performance of people. I'm honestly not sure I buy this argument. It's entirely possible, as far as I can tell, that adversarial examples do exist for humans. We just can't find them because obviously we can't directly optimize images for the human visual system, especially since people can take some object in the real world and look around and move it around on their retinas, and this helps improve robustness. And furthermore, it's not clear that there is a canonical right answer for an adversarial image. After all, you found them as the result of an optimization procedure. They're not any kind of, there's no physical process in the real world that will get a camera to produce one of these adversarial examples. But regardless of kind of the philosophical level of whether or not this is, bad news for neural networks in controlled domains, like in a warehouse where you actually do have control over what the system is seeing and you still want to be able to do computer vision, it's not clear if that's going to be a problem domain, but in the case where you do have adversaries, it definitely is a problem, and so it's something you need to be aware of. And it turns out that these adversarial examples are not that difficult to generate. So that's what this tutorial is going to be about. So if you want that, I link you to the original paper. Feel free to read that on your own time. But yes, I'm not a robot. So now let's take a look at how to generate one of these. So first, of course, we have to do the same setup, importing all of our libraries and so forth. And now we have some hyperparameters and some utility functions. And now here in this cell, we're just going to load an image and display it. And then we're going to pick a target category. So we're going to try to take this image, which is obviously an airplane, and we're going to try to convert it into a horse, basically add some noise to this image so that it still looks like an airplane to us, but the neural network outputs the answer horse. And we're going to use the same network that I used for the previous, or that we used for the previous tutorial. So again, it's a Resnet 18, and we'll define the forward pass. Here's something you didn't do for the previous tutorial. We need to actually load the state. It turns out that in JAX, you can just do this with pickle, so that those parameters and the state, which encode the network parameters and the exponential moving averages used by batch norm, respectively, those are just Python variables. You can save them out to disk, and then we're going to load them, in this case, over the internet from GitHub. And you can see that once we've run this through our network, it's going to output that indeed we have an airplane. So while it's crunching on that, let's take a look at what so it's a training image, so it has 99.999% confidence that it's an airplane. Not surprising. So now we want to actually define the loss function to do an adversarial perturbation. So it is still an optimization, but we're not going to be optimizing the parameters of the network. Instead, we're going to be optimizing the image, or specifically a layer of noise that gets added to the image in order to perturb it and change the classification. So the first step is that we're going to define this function, apply perturbation, which is going to take an image and a bit of noise that's the same size as that image and just apply it and then clip it so that it's still an image. It's in the range -1 to 1, so it's, we can't tell that it's an adversarial example just by looking at the range of values. And then from there, we need to define the loss function. And this loss function is just going to be the cross entropy loss with the training category the category that is the target, the class that we'd like to convert the image into, plus a regularization term to try to keep that noise as small as possible. Because otherwise the network might just add some huge amount of noise. It might actually add a horse to the image and that's the way it gets the classification. So we want to constrain it to be close to the value that we started with. So go ahead and write those two functions. And then once you've done that, this is some code to write the gradients. And so once you have those gradients, you can apply them repeatedly to that noise vector, this noise value that I've defined for you. And just repeatedly apply that with standard stochastic gradient descent and use that to get an adversarial example. So are there any questions?
I think someone in the channel is referring to like this kind of adversarial examples for the human brain to like the optical illusions, because we are also fooled in some situations. So there is some similarity there.
Yes, that's absolutely true. It's not exactly the same thing because most optical illusions are actually fairly large changes to the images that we're seeing. You know, you need fairly large things in the world in order to provide those optical illusions. But yeah, there is definitely a relationship there. Another real world example of this is camouflage, that animals have evolved to sort of have these patterns on their fur or feathers or whatever that makes them look like, you know, something that's not interesting, so that predators don't attack them. These don't work quite as well as adversarial examples. Of course, there's, you know, humans are fairly good at seeing through camouflage if we take the effort to look at it, but it's still kind of similar.
But maybe you can keep the code up, or you wanted to put the questions.
Oh, right. I'm not presenting a tab. Why don't? All right. I'll unpresent here and try to fix that. For some reason, I couldn't find the right window previously. Oh, somebody's asking, what is the alpha parameter? So alpha is just used to trade off between the size of the perturbation and the softmax cross entropy that you're using as your loss. So basically, your loss should be of the form, you know, the softmax cross entropy of the output network with the target category, plus this alpha parameter times the sum of squares of the perturbation that you're applying. So hopefully that's clear.
So maybe not sure if Carl mentioned earlier, like this kind of adversarial attacks, they also exist for different types of models, like semantic segmentation. They can also be attacked in similar ways, and there are papers doing that.
Is my collab not showing up?
I am seeing the collab.
You're seeing the collab?
Yes.
Okay.
I'm seeing the collab. That's what we should be seeing. Adversarial no answers. Is that the correct one?
Yes.
Okay.
Somehow I thought I had removed the no answers from the title, but I guess not.
So I guess here, like, they would have to implement the optimization by hand, like applying the steps by hand. Like we don't use the external optimizer function.
Right. Yeah, this is a simple enough optimization that basically you're going to compute the gradients with respect to that noise and then just repeatedly add that to the noise value. And you can just do that in code. You don't need an optimizer. So can you repeat, how do we perturb the noise? The noise is just a tensor that we start off with zeros. And the way that you perturb the image is to just add that noise to the image. And you're going to do it in such a way that you can use JAX to compute the gradients with respect to that noise, and then repeatedly add that gradient to the noise. So you start with a noise value of 0 at iteration 1, and then you repeatedly add gradients with respect to your loss function. And every time you'll get this noise that you can add to the original image, and step after step, that's going to gradually increase the strength of the attack and hopefully change the output category. Yes, to generate an adversarial attack for each class, you would want to repeat this procedure however many times you want to. And it's not going to be retraining the neural network. It's just retraining the, or it's going to just be optimizing that noise value separately for every category. In this case, we're just going to do it with a single category. We're trying to convert this airplane into a horse. But you can do this as many times as you want to for whatever category you'd like.
So probably in some cases, this is more like a trial and error. In some cases, to fool the network, the noise will be noticeable, right, in the input image? Or does it always find a solution where you cannot tell the difference?
This is a bit of a spoiler for the tutorial, but okay. Indeed, it turns out that you can turn that the alpha parameter pretty low, and it's still not really noticeable. And you can still, the network can end up being extremely confident that it's that this airplane is a horse.
Okay, I will post a poll just to see how people got along with the first part, and then.
Okay, so this is an interesting question. Say we get a noise value to make the network think the airplane is a horse. If you use that same noise in another image, say an image with a truck, will the network still think it's a horse? In general, the answer is no. Adversarial noise from one image will not transfer to other examples. There is, however, this notion of universal perturbations, which actually do change the classification for many different images. They turned out to be quite a bit more severe than the ones that work for a single image. And they tend to, kind of add a little bit of the texture of one particular category to another one. And so I think that these are kind of less of a threat in practice because it's kind of easier to see that they are there, but they do exist, and I think those do sort of suggest that the neural networks are looking at the wrong thing a little bit, especially in terms of looking at texture versus shape. Another interesting thing you might ask is, if you take a perturbation with one neural network and then try to feed that same perturbation in the same perturbed image into another neural network that's trained to do the same task, will that perturbation also work? And my understanding is that the answer is usually yes. It's actually very likely to fool that other neural network at least a little bit. It's generally not going to fool it as well as it did for the network that it was designed to attack, but it does do it a little bit.
60% of the people managed to implement the first part, so that's a success. I will
Good.
declare that as a success.
Although I guess it's hard to know whether it's right until you've actually run it and produced an adversarial example. How do you get labels in loss function? So you've input, as earlier in the collab, a category that you'd like to convert the image into. Somewhere in the tutorial is a list of labels. So this class dict tells you the index of each label, and so you would want to find your example in here. So in this case, the horse is going to be 0, 1, 2, 3, 4, 5, 6, 7. So you just look it up in that class dict, and that's going to be the index that you're going to feed into your softmax cross entropy. So once you've generated a bunch of adversarial examples, how can you use them to make your model more robust? One thing that you can do is just train on them. And this does a little bit to improve the adversarial robustness of the network to this kind of attack. But it doesn't actually work that well. And I think the question of how do you fix these adversarial examples is a big and open research problem. In general, what you want to do is kind of try to make sure that there's, for every training example, there's some ball around that training example where the classification is not going to change. And there's a whole bunch of math that goes into actually constraining that. And I think the details are not really that well understood. So if you want to do research in this area, that's an interesting thing to look at. Random values versus zero values. So the vanishing gradients problem tends to only occur when you have multiple layers that are zero altogether. It actually turns out that if you take a neural network that is, well initialized up to the last layer, and then the last layer is all zeros, the gradients for that last layer are not going to be zero. And you'll eventually be able to get out of this local minimum. Well, not really a local minimum, but out of this state where the final layer is all zeros. It's worth pointing out that the gradients will only be non-zero for that last layer that has all zeros. Until you've gotten rid of those zeros in the last layer, then the earlier layers are not going to receive any gradients because no information is flowing through that final layer. So the normalization to -1 and 1 is actually just, we want all the values to be in that range. So you can just clip it. And there's various functions like maximum and minimum, or various clipping functions in JAX that you can use for that purpose. You'll have to take a look at the docs to find something that'll work. Okay, I think.
Is someone complaining about the sound? Do we have a sound issue? Okay, sound is okay. I don't know why someone is saying that they don't hear.
So do these adversarial attacks work for big images with lots of features? Yes, they do. And in fact, as I understand it, it makes this easier because actually there's more directions that you can optimize the image in order to fool the network. Of course, it is harder because it's just maybe harder to fit the whole image in memory. But my understanding is that this is not, larger images don't make this harder. And why not use a genetic algorithm? Genetic algorithms are actually quite similar to any other optimization procedure in that you're sort of iteratively trying things to achieve some objective function, and you're accepting any updates that bring you closer to your objective. Genetic algorithms have the advantage that they don't rely on gradients. And so this is what's called a black box attack, which is that you don't necessarily need to know the weights of the network in order to attack it. You just need to know its output. And so as far as I understand it, genetic algorithms are pretty useful in this black box scenario if you want to fool the network. However, if you have access to those gradients, those are actually quite useful. They make the attack process happen much faster, just because you get a lot of information about which information or which directions are going to change the classification without having to do a lot of trial and error. So Viorica, how are we doing on time? Should I start showing some answers?
Maybe let's just wait for one more minute, and then you can start adding just a bit, just give away a bit of the answer, like for the first exercise, for example.
Yes, the sum of squares is going to be between the noise and the perturbed image. In this case, we're separating the image and the noise that we're inputting. So we can just take the sum of squares of that noise vector that's getting added to the input image.
Okay, so maybe we can just put the answer for the first first function.
So for this, the answer is going to be something like this. It's really just a straightforward, you take the image and add in the noise, and then you just clip it to be between -1 and 1. We use jnp.minimum and jnp.maximum. There may be more. I'm actually not sure if jnp has a clip function. It probably does, but this is just the first thing I thought of that implements this. And for the loss function, so here's how that loss function is going to look. So what's going on here is that we first find the index of the label that matches our target class, and so we can just use comparison here and then convert it to a float type, and then we use the softmax cross entropy loss that I showed you above to get our loss, and then we add in alpha times the sum of squares of the noise. So here I'll leave these Indeed, somebody found the clip function in the docs. Probably a better way to do it, just to make it a little bit more readable, but either way works.
Just to say a big thank you to the teaching assistants who are tirelessly answering questions in the channel.
So would I recommend against using 10H instead of clipping? Yes, I think I would, because in this case, we're trying to minimize the change that we're making to the image. So if we take the image, add the noise, and then apply a 10H, then even if the noise value is very small, we might end up altering the image by quite a bit, just because the 10H is going to squash the more extreme values of the input image. And alter them, and that's not what we want with this. Oh, I guess I missed a question. Why do we use the L2 metric? There are many different metrics that you can use, and I think it's, the L2 metric is really just a proxy for perceptual similarity. The most problematic perturbations are the ones that are going to leave an image looking the same, but change the output of a neural network. And so really we want to use whatever is going to sort of keep it as perceptually similar as possible. And that may not actually be the thing that minimizes the L2 metric, but it's just, in the case of this network, or in the case of this paper that I'm talking about, L2 is what they used, and it's, it works quite well. L2 also has a lot of nice optimization properties, in the sense that sort of the further you are from the optimal value, the larger your gradients are, and so that makes it sort of easy for optimization relative to something like L1 norm. I think for a lot of the modern competitions, they tend to have an L2 norm ball that you're supposed to be in if you want to, you sort of have a budget for how many pixels you're allowed to change. But there's a number of different losses that have been looked at for this, and I don't think there's really a consensus as to what's really the right one. Why does softmax cross entropy take star as an argument? That's actually just to simplify it's actually to make the code more readable. Star in Python 3 just means that anything after this point in the argument list is going to be a keyword argument and not a positional argument. So you can't apply logits or labels as positional arguments in this particular function. And so it's sort of requiring that you put those keyword labels on your inputs so that your code is more readable. Preventing model abstraction attacks. Can you elaborate a bit on what you mean by model extraction attacks? Is that like trying to figure out what the parameters of a model are just based on applying inputs to it. So where do we take the gradient of the noise? So I've already given you a function in there which computes the gradient. It may not be completely obvious from the JAX documentation how do you compute the gradient, but it's basically this here. JAX is going to, when you do this jax.grad, it's going to compute the gradient with respect to the first input of this function, with respect to the output. And so we want to minimize this loss. So when we take the gradient with respect to that, the output of this grad function is going to be the gradient with respect to that first argument that well, maximizes the loss. You're going to have to negate it to actually minimize the loss. And of course, in order to use this grad function, you need to take grad at some location in the space. And so you will need to input both the noise and the image to that loss function, or to the grad function, in order to get the grads out. Viorica, should we put another poll in to assess people's progress?
Sure. Do you want to put it, or I can put? I can ask how.
I haven't done it before, so.
Yeah, I'll just ask. Mm.
Why don't we use jnp.array instead of np.array? Not really any reason. I'm not sure if you're looking at a more specific example, but yeah, generally JNP will do anything that NumPy will do, but JNP allows for gradients. So yeah, you might as well use JNP everywhere.
Okay, we have quite a bit of no's in the votes. So maybe we'll just wait just for a few more minutes.
So I guess my question on the model extraction is just that I'm not familiar with the term model extraction. So I think, it's possible that I do know what you mean, but I just haven't heard that term used for it. Oh, So there's a question, how many iterations? So I did 50 iterations. I had a learning rate schedule that I tuned myself, but it wasn't terribly complicated. And will you see reasonable performance with alpha equals 1? Yes. So I was able to get about 90% confidence with alpha equals 1. And that corresponded to a loss of, I think, 1.43, which is in the tutorial.
Okay, some people seem to report that the image is quite perturbed, that it doesn't look like an airplane anymore, even to humans. But yeah, probably just changing alpha with the like that.
Yeah. So with alpha equals 1.0, I found that the perturbation actually was quite small. You can try adjusting it, but I suspect it's more likely to be a bug. That you're not properly constraining the norm of the noise somehow.
Maybe we could put in the code.
Okay. Yeah, I do want to leave some time for people to play around with this once you have the correct code. Here's what it should look like. So basically what it's doing is that we have a loop over iterations. At every iteration, we're just going to print out the loss function. We plug in the noise, the current noise value, which starts off as zeros. along with the image. So that's just kind of for diagnosing what's going on. Then we take the gradient function, we apply noise and the image. And now here's where I've implemented our learning rate schedule right here. If I is greater than 20, we're going to use this learning rate 0.005. Otherwise, we're going to use 0.5. And the actual update is just to take the gradient, multiply it by that value, and subtract that from our current noise value, and use that to update. So we can watch this train for a bit. And you can see that the noise does bounce around a little bit when we're using a update step of 0.5 or 0.05. But after we switch to a smaller one, then it goes down pretty smoothly until we get to 1.422. So I don't know, can one of the TAs put that in the chat so I can go on to later cells? Oops, that was not what I wanted to do. Now here's the updated image, and you can see that this image looks pretty similar to the original airplane. Here's the amount of noise, which is small relative to the values in the original image, and yet when we apply the classification, 90% hoarse. All right, so any questions on that? The final two cells of this collab are just letting you play around a little bit with the parameters of this optimization. So you can adjust the alpha value and trade off a little bit the size of the perturbation with the confidence that the classifier outputs. I was able to get the confidence to be pretty high, well over 99%, without really having that big of an impact on the image. And you can also try this with the car image that I have in the final cell. So I should point out that in this collab, for this final cell here, with this pretty ugly mass of noise, that's actually multiplying the noise by basically a factor of 10. And the reason I did that is just to let you take a look at the structure of the noise that's being created. You can see that actually most of the noise is on the object. It's not like hallucinating a horse in the background that's like really faint and hard to see. It's actually adjusting the contours in a way that's not really that easy to interpret. I think it's not really understood that well why a perturbation like this would change the neural network's output so much. Although it does seem to be, if you look at the low-level filters of a neural network, you do see patterns that are kind of like this. So it seems like it's kind of trying to drive the low-level filters in a way that puts them outside of the domain of things that these networks have been trained on, and then the network tends to amplify that noise as it goes layer by layer. But of course, there's a huge literature on, why this stuff happens and how you can avoid it. So if you're interested in this topic, there's definitely lots of papers that you can check out. There's an error in print. Unfortunately, I think the code I pasted lost all the formatting, so there should be indentations for the next 3 lines. I'm not sure how to place source code. I know in Slack you can use backticks to make well-formatted source code, but I'm not sure how to do it in Rocket Chat. Okay, how long do we have left in the...
Carl, it's similar here in Rocket Chat with the code, if you want. It's similar to Slack, I think.
Oh, is it? All right,
you have dropped an online code.
Oh, that did work.
Oh, where is that? I'm not seeing it.
So I posted it. I edited my old post.
Oh, okay, cool.
Explain how we alter the loss for a specific class. So that's going to be in computing the loss function here. You can see that it's taking the target class here. So this is a closure. If you redefine this function, it's going to look at that that target class, and so you can basically just change the value all the way up here, which is a global variable, and then rerunning the collab, it will it'll pick up that change, and the loss function will now do the right thing. Oh, in terms of math and intuition, I'm not sure there's that much intuition behind it. I mean, the math is just that you're changing the softmax cross entropy to output one particular class or another, and the Jax doing the gradients is going to automatically figure out what's the right perturbation in order to match that particular category. I'm not sure if you're asking for something more specific than that. Can adversarial attacks be applied on different modalities other than images? Yes, I think text is a little bit harder because it's, obviously it's discrete, so you can't use the same kind of gradient-based technique that we used here. However, I do know that there's works on like tweaking text using synonyms in order to produce the wrong classifications, and that does work. And yeah, point clouds, audio, I'm pretty sure they would work as well.
I think there was also a paper like on optical flow. So you can actually fool a model that an object is moving in a different direction, which is quite, and it's moving in a different direction in a consistent way, not only some pixels randomly moving around, like to have an entire object that moves consistently. So that was yeah, worrying. So yeah, maybe we can move on to the next part. So just to say, like as homework, so Carl described the adversarial attack in pixel space, but we can also create different adversarial attacks, like in the space of geometric transformations. And one simple exercise that I'd invite you to do is to take the same model that the Carl used here, so which is pre-trained. So you would load the trained model, and when doing evaluation, like we did in the baseline collab, just apply rotations to the input images and see how that affects the performance of the network, because now we are effectively changing the distribution of the inputs, but in this different space of geometric transformations. And yeah, as a spoiler, I can tell you the accuracy will drop to about 30% from 90% what we had initially. So there again, one solution could be just to add this kind of transformations to the training data set to make yeah, to have a more exhaustive data augmentation during training, such that the network gets to see those kind of examples as well. But that will be as a homework for you during the weekend, if you want to look into that. Or instead of doing training with data augmentation, I do think that if we switch to training on videos, then in videos we get naturally the data augmentations that occur in real videos. So that would help as well. But of course, training on videos brings different challenges in terms of resources. So that's yeah, a research topic in itself, how to make training video models more efficient. Okay, so I think we will move to part 3. Let me see if I can share my screen now. Let's see if I find my okay, I hope this is the correct one. So in this part, we will be looking again at implementing a network module. And this is the squeeze and excitation blocks. And we will just add this into our baseline to improve the generalization accuracy. In many works have been looking at how to better model the spatial dependencies between the inputs in a COMNET, and there are various works on spatial attention. But there are various forms of attention, and in this paper, the authors propose to look at relationships between feature channels at a global level. So, because in COMNETs we have this local information, local receptive fields, but we want to also allow the we want to use more global information when we do classification. And this is what they propose. So we have this type of self-attention, where first let's assume we have some convolutional block at the beginning. So I'm hoping you're seeing, and wait, is the code visible? Carl, can you see the code? Do you see it okay? Or do you see the
Sorry, I was looking at the chat. Yes, I can see.
Okay, so yeah, thanks.
Yeah, you might want to make it a little bit bigger, but I can see it.
Okay. So these are figures from the paper, from the squeeze and excitation paper. So as I was saying, you just add these blocks into an existing model to allow the model to reason about dependencies between the feature channels. And we can reason, and we extract global descriptors and then we use this to recalibrate our feature maps. So effectively, what is happening? We have a block of feature maps, and then we apply the squeeze part, like the squeeze part of the module. Here we extract these global descriptors for each feature channel. Then we apply a sort of a gating mechanism, an MLP, such that here we extract the dependencies. We compute weights to recalibrate the feature channels based on the relationships between them. So this will result in emphasizing some of the feature channels, or putting less importance on other feature channels. So basically, here, and as a squeeze function, the simplest that could be used is you can just do a global pooling over the spatial dimensions. So this then will just give you a vector of weights, just give you a vector of statistics that has the dimension 1 × 1, 1 by 1 by C, and C here is the number of feature channels. And then we apply the excitation gating mechanism, and this will give us the output weights for recalibration. And to make it clear, so here in the second figure, we have the exact modules that we need to use. So this is how we apply it in a residual module, like we've implemented already. So basically, you just take your feature maps. At the end of a Resnet block, but before doing the addition in the Resnet block, and you do the global pooling over space, and then you apply a linear layer or a fully connected layer with a reduction factor, because otherwise this could be computationally heavy if we keep the same number of channels or even larger. So the authors use a reduction factor, and this is defined as a parameter as a hyperparameter of the model. And then we apply here a nonlinearity, and then we have another fully connected layer, and then we have a sigmoid. So we don't use softmax here because we want to allow multiple feature channels to be emphasized, not only one. So this is like a very simple form of self-attention, and once you get this vector of weights, then this gets applied. We broadcast and we scale the input feature maps. So this is a very simple form of self-attention. You will see later at the school presentation on transformers, which is very popular now form of self-attention. So in this the exercise for this part, you just need to we have again the same part. So we have the imports and then the data set, but please do run the cells. Okay. Okay, we might be running a bit out of time. So I've defined here the reduction ratio that we will use inside this squeeze and excitation block. So the rest are the same hyperparameters as before. Nothing has changed. And then we load the data set and the pre-processing as before. And then here we have the squeeze and excitation block, which is the coding exercise for you. So again, we are just defining a new class, and I've already defined the layers that you will need. The layers that so in Haiku you need to define in init the layers that have parameters, and then in call you just you link them to the computation. And then in call, you can also use any other functions that do not have parameters, like rarely. You put them directly in call. So yeah, here you just put the code. So just follow the schematic from here. So basically, first you just do a global pooling. And for the global pooling, you can just use the mean. If you can just JMP mean, that will do. So let me see if maybe I haven't shown. So when you're not sure, I'm sure you've discovered, but when you're not sure about the syntax, you just type the function here and you put a question mark, and then if you run that cell, it should. I'm not sure if you see it. It will bring the docs for that function. So yeah, to do the global pooling there, you would use you could use JNP mean, and this is the signature of the function. You have it here. I think there's a question, how is mean across channels adding value? So if you could, I don't know, imagine different feature channels like colors, for example. I think there's it's not an accurate example, but there's that famous video with the gorilla, and you're asked to follow a white ball, and then a black gorilla passes by, and you don't notice the gorilla. So you can have a mechanism that allows you to emphasize a certain feature map, right? Like in this case with the gorilla, you're interested in following the white ball, so you would pay attention to the feature map corresponding to the white color, and you might ignore completely other feature channels. So in this sense, extracting this kind of global information can still be useful. Global pooling in Jack, so I've just I've shown the JNP mean. That should do. Does the self-attention in the model affect the ease of finding adversarial attack examples? That's a good question, and that would have to be tested.
I was just thinking about the same thing, and I'm not sure whether or not it would. And I agree that you probably have to test it. My feeling is that for most models right now that haven't been trained specifically to be robust to adversarial examples, it's actually pretty easy in all cases to make it to make adversarial examples. So I suspect that adding attention versus not is not going to make that much of a difference, because I think that adversarial examples are a little bit orthogonal to the inductive biases in the network. because they're kind of going off the manifold of things that have any corresponding physical realization.
So yes, maybe just to clarify, maybe this is confusing. So these two parts are quite independent from each other. This self-attention part and the adversarial part, they're independent exercises. Is just to show you different, one way to improve generalization in your network. And as you will see later in the code, this is actually a very easy and cheap way to add more expressivity to the network. So I guess as exercise, so yeah, once you implement the block, we would just have to add it into our previous ResNet block that we implemented. So we just define it here, and then we have to add it in the ResNet block before the addition. And the rest, would stay the same. So regarding adversarial examples, I think one work that I've seen to help against adversarial examples is to use distillation from a teacher model, and to train with training with soft labels helps when, it makes the models more robust to adversarial attacks. Because when using soft soft labels, we don't expect all the classes to be orthogonal, to all the class representations to be orthogonal to each other. We allow the student model to learn some correlations between the classes, and maybe that leads to a better clustering in the output space. But that's still very right. So yes, self-attention does not use keys. Indeed, so this is, as I said, you will see the transformers next week with the full self-attention. Here is just a very simple form where we just use this gating mechanism to compute calibration weights for the feature maps based on the actual inputs. So we are attending on the different feature channels in this way, putting more emphasis on some and reducing the importance of others.
So I think that the reason why this squeeze excite idea works is not that well understood as.
Okay, everyone, we have a small problem. I think Carl got disconnected. Let's just wait for a few seconds for Carl to come back. Okay, yeah, he's back.
Strange. So yeah, where was I? So as is the case with a lot of neural networks, we can't really say exactly what one particular channel in the network means, but there's a number of reasons why you might expect that some kind of information about the global state of the image would be useful for interpreting it. For example, imagine you have an image where you have a small dog, and then you have a lot of foliage in the background. And you know, maybe that foliage correlates with one category or another. You know, it's more likely to be you know, some kind of outdoor breed of dog versus an indoor breed of dog if there's foliage, but that's actually not that relevant. And so what you can do with this kind of global attention is to realize that those features are not useful and sort of suppress them across the entire image, and then pay more attention to the features that actually are relevant. Another possibility is lighting. Of course, you're going to have the same lighting throughout the whole image. And so maybe you want to be able to realize that, okay, the lighting is coming from this particular direction. You can infer that from one part of the image and then transfer that knowledge elsewhere in the image in order to more accurately interpret the more difficult parts of the image. Of course, these are just stories that you tell yourself to understand why the performance is going up. The empirical fact is that this does improve performance, at least in some cases. So that's kind of why we study them.
Okay, so I think we're kind of running late, so I will put in some of the code because we have the welcome drinks soon. Let's see where are they? So yes, as I said, we first apply average pooling over the spatial dimensions, and then we have the two fully connected layers with nonlinearities, and then we just multiply the input feature maps with the weights obtained from the block. And then when we go in here in the Resnet block, we simply call the block that we've implemented with the right parameters. Then we link it in the call function. Okay. Okay, so I think we will leave in some 2 minutes at most. So you've all received the invitation for the Zoom social. I hope you all have it. See if I can run quickly some of the blocks. Okay, it's going to take again the data set because I restarted my Colab. Okay, so yeah, we should probably leave now the call. Sorry that we didn't manage, but yeah, this is just running now the rest of the code, and yeah, also looking at the difference in the number of parameters, and you will notice that the increase is actually very small. It's less than 1% increase in number of parameters. But you do get a better test error.